2, Part 2, Harmonics. Our panelist today is Dave Deal. Quick reminder before we start to everyone, all attendees are muted by default, so if you have any questions or comments, please type them in the questions tab. And with that, I would like to introduce Dave Deal.
Thank you, Alex. Before we start, I'll say that Richard A. is assisting me in the share my screen in this presentation, so he's going to be answering these questions as they come in. And please keep your questions on topic. We're not here to answer your day-to-day Seizure 2 questions, but this is on harmonic analysis and Seizure 2. It's pretty much a show and tell. If we have time at the end, I will run through the program quickly, and if there's time at that point, we'll also field some interesting questions that Rich will bring up. Our agenda, after a quick overview of harmonics, we'll take a look at the static model that I'm going to evaluate, and then we will create the harmonic input. We'll take a look at the actual harmonic analysis itself, and then review the results. And I think an important thing of running harmonics in Seizure 2 is this analysis adjustment idea here. You don't have to just take the numbers that the program gives you. You might be able to, well, you'll search for the numbers that you want in the results. And then we'll close it up and look at those questions you might have. On the overview, cyclic loads, even if they're a small magnitude, can damage your piping system. And just about everyone's concerned about a piece of pipe that's shaking around out there in the field. Is it going to fail? So Seizure 2 can be used to replicate the piping response to those harmonic loads. And the key here is that once we get the computer model to match the physical system in the field, then we can confidently adjust the model on our computer to detune the system and assume it's going to work well out in the field, that fix. Now, what we're going to focus on here today is the forcing frequency to natural frequency ratio. Some type of applied loads at a frequency and a natural frequency of the piping system. When they coincide, that's when you get this resonant vibration. We're not going to be looking at evaluating a calculated fatigue stress amplitude. That's not the purpose of this webinar. So what we're going to do is we're going to develop the Seizure 2 input required for harmonic analysis and touch upon the engineering concepts that are involved in getting us there. We'll also take a look at some of the intermediate steps used in the analysis. Okay. This webinar will not address the source of harmonic loads and their evaluation. This webinar will exercise the harmonic processor. So I don't want to see the registration count go down right now because there's still a lot of good information here. All right. Now, for initial design of, and this kind of covers what we had in our last dynamics webinar, you will basically try to avoid problems by controlling your lowest mode of vibration of your piping system. If you know what kind of excitation frequencies you have out there in the field, you will try to avoid them in that initial design. But that's pretty much a qualitative type of analysis rather than a quantitative. You're just calculating a frequency and say, oh, I don't want to have that frequency in my system. Not saying this is the stress caused by that harmonic load at that frequency. That's pretty much wasted effort in the design field. But we do have problems out in the field, and we talk about this in our seminar. We talk about different sources, mechanical vibration, flow-induced vibration, and pulsation in your piping systems. Now, in mechanical vibration, your mechanism, what causes the load in the system is basically cyclic displacement of a boundary condition. Typical example is a pump nozzle vibration. There's some imbalance in the equipment, and the nozzle itself wags back and forth at a given frequency, and that excites the piping system. Flow-induced vibration. This is a force in the piping system, and usually the vector that we would apply in the system would be perpendicular to the direction of flow. Flow across the pipe or flow through a restriction in the pipe like a orifice or something like that. And finally, pulsation. Again, this is a force applied to the system. Again, we have displacements or forces, harmonic displacements or harmonic forces. These pulsation forces are basically in the direction of flow. It's a change in pressure in the line, reciprocating systems basically. So what we're talking about here are problems in operating systems. These are forensic engineering tasks, not design engineering tasks. The problem is actually in the field at the moment, and we have to try to evaluate it and perhaps remove it. Okay. Now, the one advantage we have that we might say it's an operating system. The advantage is that make the bad good is that there's actually a real system out there in the field that we can then benchmark our computer model with. Okay, it's very difficult to predict the actual natural frequency of a piping system because there is a variability in the stiffness of the system and the mass of the system that we use. Okay. Now, if we talk about forced harmonic motion, it's the ratio that's important. The ratio of the forcing frequency, we can pretty much establish that, the pump vibration or something like that, with a natural frequency of the system. There's many natural frequencies, so we can rate that as omega, the forcing frequency, divided by omega n, a natural frequency. So if we do the math on that, we end up with, let me get rid of this here, with an equation. This is the textbook I used in college, Theory of Vibration with Application by Thompson. The amplification is a function of the ratio of the forcing frequency to natural frequency and also the percent critical damping. Okay, this plot here shows this equation exercise for 4 different percent critical damping: 1%, 3%, 5%, and 10%. And you see when you get to 1% and you're running it right at the natural frequency, you get a multiplier of 50. So it doesn't take a large load, a large imposed deflection to get a large applied load to get a large amplification. Now in piping systems, they run, I'd say, from 1 to 3%. If you look at some of the newer codes, they talk about using 5% critical damping for piping systems. I believe that's mainly for the seismic load evaluation, not so much for the actual frequency response of the system. Well, we might be able to guess the forcing frequency, that omega. That could be the speed of the pump that's pushing the system around. But we're not going to get the natural frequency right. Again, the natural frequency is a function of the stiffness and the mass of the system. And who knows what the stiffness of that support is? Who knows what the actual mass of that valve is in design mode? Once it's in the field, you can start to estimate these values, but it's very difficult to get this one right. So what we're going to do is try to do our best job at guessing, I'll say, that natural frequency. Now what we're going to do, though, is going to be our trick here, is that we're going to, even though we might know that omega, we know exactly the speed of that pump, we're going to adjust this omega in order to force this ratio to get the field response. Again, we're going to focus on the ratio. Now, if you can match the shape of the system out there in the field, you can gain confidence in the bending components and therefore the stress in the system. Again, we're going to run Caesar 2 to match the shape of the entire system that we see out in the field for this harmonic event. One very important note on the applied harmonic load: do not enter an observed response as your input load. Determine the load source and use that to develop your load vector. Again, do not use an observed response. If you see an elbow wagging back and forth, let's say 1/2 inch at a certain frequency, that is an observed response. The actual load could be caused by the 3 items we mentioned: a pump vibration, pulsation in the line, or flow-induced vibration. But in no case, there's no reason to believe that that elbow that you see is what is causing the load. That is an observed response. A very important thing. Now, the model I'm going to run today is a rather simple model. Of course, we always run simple models. I've got this piece of rotating equipment. I'm not going to tell you what it is. I'm not too interested in the actual numbers here or the causes of these. But I'm going to say we see this elbow at 1050 wagging in the XZ direction when this piece of equipment is running at 330 RPM. Okay? So what I'm going to analyze then is this side of the piping system. My load is going to come in at 1090, and I'm going to try to match the deflection that we see at 1050, 1049 in the field. Okay, that's my model. Now let's look at the harmonic input that we're going to create for this. Well, I'll open up the dynamic input processor procedure 2, and again, if we have time, I will go through this process, and I will either click on the app once the model has been built and static a solution achieved if it's nonlinear. I will click on this button, or I can click on analysis, click on dynamics. There's that same icon. Okay, it'll take me in then to the dynamic input processor, and I have to select the analysis type. Well, of course, I'm going to select harmonic. Once I select harmonic, then I will have the tabs associated with harmonic analysis. Now, these tabs, we'll go through them one at a time before we get, well, let's go back here. We will define our forcing frequency. This is that omega that I was talking about, or several of them. We will either define a force or a displacement. This is the applied load. We can adjust the mass model, and of course we'll control the solution here. All right. So on that toolbar, we have a couple buttons here. I can save my data, I can error check the data, and I can run the analysis. Of course, that running man is the one we're going to use to submit the analysis. Every tab will have a couple of lines in it. Here we show the excitation frequency. There's 2 lines right there, 0 and 1. And I can add more lines, or I can delete lines from my data set by using these plus and minus buttons up here. I also have comment lines. You see, these are both comment lines, a check point, so the program will not try to interpret that data on that line. Now, the first thing we're going to do is enter excitation frequencies. And we see we do have a line here with the excitation data, okay? We have a starting frequency, an ending frequency, and an increment. My initial assumption is that the equipment is operating at 330 RPM. Well, this is in hertz, so I divide that by 60, and I get 5.5 hertz. Now again, we're going to focus on the ratio of a very well-defined omega, that's this omega here, but an uncertain omega n, okay? So what I'm going to do is I'm going to sweep through these omegas. It's like turning the knob on the old analog radio, trying to tune in a radio station. I'm just going to tune it until I get the radio station I want to hear. I'm going to tune my forcing frequency. It's kind of backwards. I'm going to tune my forcing frequency so that I get the resonance that I see in the field. Now, what we suggest is that you sweep about plus or minus 10%. So if I'm running at 5.5, I'll go down a half a cycle and up a half a cycle. So I'm going to run a forcing frequency between 5 and 6 hertz. So my data here is starting at 5 and ending at 6 hertz, and I'm going to stop at every 0.05 hertz. Okay? So I'm going to run an analysis at 5 hertz, 5.05, 5.1, 5.15, and so on until I get to 6 hertz. This will give me 21 separate analyses, all with the same load, but each at a different frequency as we adjust this ratio here. We're going to talk about this load cycles later. OPT, that means optional, optional, optional. Now, if I just specified a value here, that would be the only analysis I do. Okay? So this is my excitation frequency. So that's my omega that I'm going to use. Now, in terms of defining my load or displacement vectors, again, this is a vector we're putting on the model. Somewhere in the model, it's going to be either a force or a displacement, one or the other. Okay. If I'm doing pulsation or flow-induced vibration, it's going to be a force. If I'm doing mechanical vibration, it's going to be a displacement. Here, I'm going to put a 0.1 millimeter displacement in the x direction at the anchor at node 1090, right there. It's an anchor, but I'm going to put a 1/10 of a millimeter deflection on it. Okay, so I specify the magnitude, direction, and the node. That puts it in space at that point right there. And I'm also specifying a phase angle. A phase angle is rather arbitrary here, but basically what we're doing is we're applying a cosine wave as our load. When this initiates, it's going to be deflected a 1/10 of a millimeter. It goes through 90 degrees, and it's going to be 0. Then another 90 degrees, it's going to be minus 0.1, and back up and through a whole cycle. Okay. There's other systems. If you have, let's say, 2 cylinders in a compressor unit, they might be out of phase. I'll have 2 different vectors, and they will have a different phase angle between them. This phase angle will become quite interesting later on, but right now, just phase angle of 0. Now, the next tab, the excitation frequencies, we've got our displacement. I'm jumping over here to the control parameters. We're going to breeze over this pretty quick. We have no nonlinear restraints, so I don't care about row 1. I have no friction, so I don't care about row number 2. Damping. Now, this is our true wild card here. I'm going to say it's 1% critical damping. Okay. And I'd say rather difficult to predict what it actually is out in the field, okay? Because if we look at that chart I had before, we can really zoom up the response if we say it's 1% versus 3%. But bear in mind, we're trying to reproduce a deflected shape that we see out in the field. And if it takes me 1%, well, I'm going to use it. 3%, we actually have 3 different terms that we can vary to affect the total response. 1 is the load that we applied, 2 is this damping term, and 3 is the ratio of natural frequency to forcing frequency. If my ratio is, using the red line, if I'm running it right at its natural frequency, my multiplier is 50. If I detune a little bit and come over here to, let's say, 1.1 in the ratio, I'm down to only about 10 times. So adjust these numbers to match the field response. And finally, the last item, I'm going to use consistent mass. It's more accurate rather than lumped mass. Okay. Now, what about the other items? I didn't mention anything about these lumped masses and snuffers. Well, catch up. We did that in the modal analysis webinar presented back in May. If you wish to view that, it is available online on our blog. There's the address if you wish to go there. Or you can just, dig down through our old website, follow support, insider blog, webinars, and then scroll down to that webinar. This webinar, too, will be posted there sooner or later. All right, so we got our data set and ready to go. Let's now talk about getting it in the Caesar 2. A little more on damping. If I have a system with no damping, and for many years Caesar 2 did not have damping in the harmonic solver. Usually damping would be handled in seismic analysis as a reduction or increase in the applied load, not in the response of the system. But now with damping for harmonic analysis, we can have damping affect the dynamic solution. So here's a little engine that's spinning around here, and it's just wagging this plate back and forth. And if I have no damping in my piping system, I get this, let's say, a fishing rod stuck on that plate, and it's going to wag back and forth too. With no damping, it's going to wag back and forth right in time with the applied load. So as the base gets through a cycle, the tip response is getting at the same point. Okay, no damping. There's no delay in the response at this end compared to down there. And that's an in-phase response. The phase shift is 0. In real systems, though, there is damping. And with damping, we're going to find that there's a delay. When this base is going to the left, the tip is trailing behind a little bit. So when this gets to its peak, its maximum deflection in this direction, this is still trying to get out there. So I'm going to see this phase shift in the response. If I look at the base, and if my base is at its peak over here at the most positive point, the tip won't get to its most positive point until some angle later, some phase angle or phase shift after the peak up here. That's what damping will do to our response. Now, I am not implying that we have the exact same magnitudes between these two. These are normalized shapes. Okay. Now, a often used term in Caesar 2 for harmonics is a frequency phase pair. Okay. As part of the dynamic harmonic analysis, Caesar 2 will identify the phase angle that produces the greatest resultant displacement for each frequency analyzed. So the program will say, okay, the maximum deflection of the tip is, 3 millimeters, and it occurs, I don't know, say 45 degrees after the maximum of the base, or in our case 1090. So it'll identify that phase shift. So there's a frequency and a phase shift. If you change frequency, the phase shift will change as well. These frequency phase pairs for the greatest displacement anywhere in the system are offered as individual reports in the output processor. It says here, think of these as snapshots of the system. I'm just snapping a camera at an instant in time. This is the position of the piping system. I've got all the nodes in space and their positions X, Y, Z. I've got all the forces and moments. I've got the stresses in the system. Okay, but it's only for that instant that produced the greatest resultant displacement throughout the entire system. If your interest lies with other points in the piping system, you can select your own frequency phase pairs to be reported. Okay? Let's get through this stuff first and we'll come back and talk about that. So here, once we push the button to run Caesar 2, we get this screen. All right? We have I was just asked to move my hair. Alex, get on the phone here. I want to see if this works. You let me know. I'm asked to move my presentation to the other screen. And tell me if this works. Well, I can't. No, I'm not going to move my presentation to the other screen. Sorry. Watch the video. I'm sorry. Excuse me. We had asked for 21 different analyses from 5 to 6 hertz. Okay? And here they all are listed. That's the 21 analyses I requested. The program shows me which node had the largest deflection. And that's 1049, right at that elbow. It's right near that node 1050 that we had earlier. Okay, the node with the greatest displacement is the same for each frequency. Sometimes, depending on the model, this will change, but right now it's all the same node. And then it lists the node's maximum displacement. Okay, so if I'm running this at 5 hertz, node 1049 resultant displacement is 0.1777 millimeters. Okay. And if I'm running at 5.5 hertz, it's now at the 0.7 millimeters. The next column is the phase angle that gives us that maximum deflection. Okay? And these other last two columns are a different way of viewing this response. I mentioned earlier, like it's a cosine wave. Well, this is reflecting a cosine wave. But we can also go to a real and imaginary coordinate system here where I look at that vector and the vector just spins around this origin and it goes from real to imaginary. So if I just plot this back and forth on the real axis, that's my cosine wave. Okay, I pretty much explained that and I just ignore it because I'm using these values over here. Let's take a closer look at these numbers. Okay. Here I am plotting the response of all these items here for different frequencies, okay? And note what happens. Now again, the applied load at node 1090 was only 0.1 millimeters, okay? And at 5 hertz, I'm getting 0.177. Now that implies some amplification anyway, right? Because if I put a static load on that anchor of 0.1, this will be much smaller. But we see here, as we increase the forcing frequency, we get through a peak, and then we drop down on the other side. There's our peak right there. Okay. I can also see my phase angles. All right. At 5 hertz, I have a phase shift of 5 degrees, and up here at 6 hertz, it's 170 degrees. All right. So we can see that there is a phase shift associated with our response. Now, here's a great hint here. Look at the largest value at 5.65 hertz. Look at that phase angle, 90 degree, almost 90 degrees. I will tell you that the mathematics will give you a natural frequency when the phase shift equals 90 degrees. When the phase shift is 90 degrees, you are at a natural frequency. So I'm going to say there's a natural frequency in my piping system right around 5.65 hertz because I'm right there at 90 degrees. Okay? There's our maximum value. So here's our frequency phase pair. There's the frequency, 5.65, and that's the phase angle, 90.45. It is going to give us that one because node 1049 moves over 2 millimeters resultant at that point in time. So if we click on the OK button in Caesar 2, it'll then take us to this screen. And now I'm going to say, oh, since I don't want to read all this stuff, I just look here and I say, okay, let Caesar 2 select the frequency phase pairs. We're going to talk about this later, but right now when I push that button, it's going to ignore this stuff. So I push that button, and now I'm into the final screen before I get to the output processor. Here are the 21 frequency phase pairs that I selected, or were selected for me, 1 through 11, and then 12 through 21. Here's the one that I'm interested in, number 14, 5.65, 90.452. Why am I interested in that one? Well, that's the biggest one, okay? So when we say OK here, we are then taken to the output processor, and we'll take a look at the results review. All right, so here I am in the output menu of Caesar 2. This is a harmonic analysis, but if you've never run dynamics, you would say, oh, that looks like a static output screen. Well, to tell you the truth, the harmonic solution is a static solution. We won't get into that now, but basically here is the report I want. So we're using the static output processor. The 14th load case, there's the 5.65 hertz at 90.45 degrees phase shift. That's 90 degrees off of the maximum at node 1090, our input node, our loaded node. Okay. So the program picked these for us. I didn't pick these. Let's take a look at some of the numbers. I'm going to look at the displacement report for that load case. I click the View Report button, and here's my output. There's the title, displacements at this frequency phase pair, right? Now, I really don't have anything to look at here except really node 1049. And if you recall, in the report, it said it moved 2 millimeters. Well, I take the sum of the squares of those three deflections, and it equals 2 millimeters. Yep, this is what the report had earlier, and it matches, okay? And it's at 1049, and it's at a phase angle of 90 degrees off of the frequency 5.65 hertz, okay? So this is reflecting this summary that we saw earlier. Let's take a quick look at the restraint report. See what's going on here. If I click on the restraint report for the case 14, I see a pretty crazy number. What's with that giant number, 1090? That's where we supplied the displacement. Now, 1090 is an anchor. It doesn't want to move. So when I pull on that anchor, no matter how much it is, I'm going to have this huge stiffness to contend with. And again, this is just Caesar 2 reporting. It says you got an anchor there. If you pull it 1/10 of a millimeter, you're going to get a large load. Now, what is the deflection of that anchor? Remember that we are not looking at the anchor moving 1/10 of a millimeter at this point in time. We are 90 degrees off of that maximum. So it's going to be 0.1 millimeter times the cosine of that angle. Okay? So when we take that as our deflection times that stiffness, we get that number. And again, these are big numbers. It's not, you do the math directly, you're not going to get that number, but it's going to be in the ballpark. Okay? When I go to the internal forces and moments report at node 1090, there's only a 92 Newton load in there. It's not this. This is, I call it the hand of God moving the anchor back and forth. What does the pipe see? It sees only 92 newtons. Okay, so don't let that number scare you. Easy for me to say. Okay, on the stress side, let's look at the stresses for that load case. Here's the the load case we're looking at? Well, here's some stresses, but look at this. That allowable stress is, we're running B31.3 here. That allowable stress is the limit for sustained plus occasional, 1.33 times the hot allowable stress. Do we want to do that for a harmonic load? It's called an occasional load. That's why we're doing this. But no, stop. We don't want to do this. If we're going to evaluate stresses, that's not the stress we want to look at. Okay? Stress limit we want to look at. So let's review this a little bit, type of stresses we have here. Now, B31.3 considers occasional stresses like harmonic loads as force-based loads and therefore subject to collapse. When 31.3 evaluates occasional stresses, it sums them first with the longitudinal stress to sustained loads, and those must be less than 1.33 SH. So that's where we get our 183 megapascal as our allowed limit. But we shouldn't be looking at harmonic loads as a collapse type load. Instead, we should be looking at it as fatigue basis. Now, I said we won't evaluate these stresses, but I just want to pull out this quote. I'm not going to say this is the latest edition of API 618, but it states, pulsation-induced vibration and or mechanically induced vibration shall not cause a cyclic stress level in excess of the endurance limits of the materials used for components subject to these cyclical loads. Okay? Goes on to say that for carbon steel pipe, like we have here, the peak to peak, this is a good term to get under your belt, peak to peak as opposed to zero to peak, stress range should be less than 179.2 megapascals. Okay? Considering all concentration factors and with all other stresses within applicable code limits. Now, Caesar 2 isn't doing this, and it doesn't have anything to do with concentration factors, okay? What we're showing you is a stress state at a specific phase angle, and at most, that might be zero to peak, but there's no stress concentration factor. And what of the stress formula we used here? We're using the code equation of MI over Z. Is that appropriate for fatigue analysis? Well, we're going to have to fix that. We're going to do some adjustment now. I'm going to go back into the input processor and establish a fatigue curve. Now, if I look at fatigue analysis in my, first let's set up the fatigue calculation in our harmonics. Now, earlier I said we're going to come back here and specify load cycles. This is that very first input screen, excitation frequencies. If I specify a value here, the load cycles that I'm requiring this to go through, the program will then convert from an occasional to a fatigue analysis. It will also use a von Mises formula or equivalent stress formula rather than the code-defined stress equation. It will then go to a fatigue curve that was specified in the input processor, which we didn't do yet, and establish the stress amplitude for that value. What we're going to do here is we're going to specify 100 million cycles, 10 to the 1E8. I don't like counting zero, so I don't type 0. I type in 1E8, all right? And run that. Well, if I look at my output processor, you might recall earlier this said OCC for occasional. Now it says FAT. So I run the analysis again, and this has changed. And the formula has been updated. It's very similar. There's very little difference between the code stress formula and the von Mises or equivalent stress calculation that we're showing you here. For example, at node 1020, it now 5.67 megapascal. The other analysis was 5.66, so it's not a big difference here. But we don't have an allowable stress. Why? Because we did not specify a fatigue curve. So now let's go back and get that fatigue curve in the model, okay? All right. Here is a fatigue curve. I put this together from ASME 2011 addendum to Section 8 Division 2 Part 3, Annex 3F, Design Fatigue Curves. this is pretty much boilerplate information from other fatigue curves that we ship with Caesar 2, but I put this data in down here. This is my low carbon steel, polished steel. Again, we don't have any concentration factor in here. That's not the subject of this webinar. Okay. Now, how do I get that in the Caesar 2? Now, this is the input processor. I'm looking at the very first piece of pipe, and there's my B31.3 limits. I click on this fatigue curves button at the bottom, and I get this window coming up, and I can type in the stress allowed for a certain number of cycles, or as we would normally do, click on that read from file button, and it will then ask us what file do we want to read in. Now, I don't want to confuse things, but we are now in the static input processor, and this would be the fatigue stress limits for range calculations, not amplitudes. Harmonics is amplitudes, expansions are ranges. So actually the numbers that are end up here will be peak to peak rather than zero to peak, but I'm getting ahead of myself. I'll click on that button, and that'll take me to the Caesar 2 system folder where the files that we ship for this purpose are located. Now I could use 5-110.1a from the old code, but here's the one that I built. So I'm going to select that one, and it brings in the data. Now the data that I showed you earlier was in PSI, but this job's a metric job, okay? So it converted them to my current units, all right? That's my fatigue curve for my material, all right? So now that's in my static model. I do the error check and analysis and statics, and now when I go to dynamics and run the analysis again, there's my allowed stress level. Okay, that's based on that fatigue curve. That's my stress level allowed for 100 million cycles. Now, if you recall that quote I had from B16, API standard 618, it said that the peak to peak should be less than about 180 megapascals with zero to peak of 90 megapascals. Well, I'm less than that. This one is now saying 68 megapascals. Okay. Now, again, look at these numbers. Here's the highest stress, 5. We're only using 8% of the allowable. That's not the point of this session. We're talking about getting the data into the program. All right. So now we got a decent fatigue analysis, except for that concentration factor. I have one other item to discuss here, and that's the selection of frequency phase pairs. Recall in the program that we can take a look at unique frequency phase pairs rather than just the default ones that the program gives us. Again, this is a dynamic analysis. The system's moving. All right. The results that we have in our output file are at a current state at an instant in time at a specific phase angle. Things are always changing. Again, think of it as a snapshot of the piping system. I snap a picture and I evaluate the state of stress in that picture. Okay? Caesar 2 can provide several snapshots of the piping system as it goes through one cycle of harmonic response. Now, we looked at the reports that the program gave us by default. It would be the report for the phase angle that produces the greatest resultant displacement of any node in the system. That's what's reported in the output, okay? But what if you're interested in some other point in the system? Okay, here's that screen. These are the 21 that the program selected for us, okay? And usually people say, okay, I'll take a look at that. But there are other reports that you might want to generate for other phase angles at these frequencies. You might be interested at a different point other than 1049. Okay? How do you do that? And let me say this too. There is no guarantee that the instant of maximum nodal displacement corresponds with the greatest stress amplitude. You could be working on some T that's cracking and it's not reported as a maximum displacement point in the system. Well, you should go look at that T instead and find out when the largest moment is on that T. Okay? You can select your own phase angles to be displayed with each frequency based on the deflection of any node in the system, not just the maximum node. Okay? Now, we're back to this screen. Remember I said, oh, blah, 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 I don't want to read this text. Well, now I want to read it. Instead of having seizure to select the frequency phase pair, I want to select the frequency phase pair. All right? So now this becomes important to me. A phase relationship exists in this solution because of a damping. Okay, I had 1% critical damping. In a phase solution, the maximum response can occur at any time during a system cycle, ranging from 0 to 360 degrees. Okay. We had 21 frequencies. Each frequency can produce 18 phase solutions. Well, I could click them all and get all kinds of load cases here. Well, let's be smart about it. Let's select some. All right, so the program, since I select that button here, the next screen comes up and says, okay, it says, which frequency do you wish to evaluate? Now, you recall that the 14th frequency, 5.65, produced the largest deflection in the whole system. That was the closest to resonance at a phase angle of 90.45 degrees. This time I'm going to select number 13, a little off, okay? So I select that. And if you recall, on that one at 5.6, my phase angle is 48.98 and my maximum deflection is 1.5 at 1049, okay? So what I'm looking at now, if I wish, I could look at this one. I'm going to take a look at 5.6 hertz, okay? So I select that one. That's the frequency. Now I select the phase pairs, okay? So the next screen I see is this screen here, and I type in a node number that I wish to review, and it dumps in all the data here for that node number, okay? Here are the 18 phase angles that are available for this frequency, giving us the output for that node. All right. Now, 18, we've got 360 degrees divided by 20, that's 18. So it's every 20 degrees. 0, 20, 40, 60, 80, 100, 120, 140, 160. But you notice that some of these are a little off. What's going on there? Well, again, here is, all right, is that magenta? I don't know. That line right there is not the orbiter going around the Earth. It's the deflection, normalized deflection at node 1090. That's my 1 millimeter, 0.1 millimeter, going 0.1 to 0 to minus 0.1 to 0 back to 1, okay? And I have these 20 report times available for my system. Well, I'm focusing on 1049 now, and here is that phase shift of 1049. It's lagging by about 49 degrees. So when that is at its peak, there's the peak right there, 49 degrees later. Now, here are my 20 different reports that I can generate. So I'm going to put them on my plot. Okay, there are my 20 points. Okay, so I can get a report at all these. But now I got a little problem here. Don't you think I'd be more interested in that point than one of these? Or this point rather than one of those? Go to that peak. So what we can do in the program, or the program will do, is it'll find those peaks, maximum positive, maximum negative, and the 0 points. And then it'll shift the response at those report times to match with those 4 values. So the 3rd report is at the peak. The 8th report is at 0, or close to 0. The 12th is the negative, and the which one? The 17th is back to 0. So now we can select these. We click on these index numbers to say we wish to use them. So yeah, I already double click the index values to generate report. There's a star. I already picked these 4. 1, 2, 3, 4. I picked those because they are the 4 most interesting reports. Okay. If I picked a different node number, again, damping would have some of these phase shifts different. Okay. Now here's the maximum value for this one. In the X, 1.04, in the Y, 0.1, the Z, 1.08. Take the squared sum of the squares of those, and that'll be the maximum response. Okay. Now, I click the button, and again, I have 4 frequency phase pairs in my output processor. Okay. It's all the same frequency, just at 4 different phase angles. So I go to my output processor, and there's my 4 frequencies, and there's my 4 phase angles. Again, frequency phase pairs. Now, I built on my machine my own custom report. It's a displacement summary. It's kind of like this restraint summary up here, but allows me to review numbers for displacements for all the load cases selected. So I can see them side by side. So I'm looking now at that report, displacement summary report, various load cases, 1, 2, 3, 4. And let's just look at the X direction. Again, this is all for 5.6 degrees or something like that. At this one, it's 1.04. This one is minus 0.01. Here it's minus 1.04. And then pretty close to 0 here again. So go positive 0, negative 0. Positive 0, negative 0, and so on. And if I add these up, square some of the squares, I get to that total listing that was in the summary to begin with. Okay, so the displacements are changing through the cycle. This again highlights the fact that you have to find the maximum stress before you can evaluate that stress amplitude. Each one of these will have its own stress level too. If I use the wrong report, I might assume that's the amplitude. No, you have to find the maximum amplitude, and the source or the method we will find it is through this maximum displacement or this displacement. Okay. If I look at the stresses for these 4 cases, again, reiterating that point, it's all the same frequency. It's just when we snap our camera. There it's 4 megapascal, it's 0, factor 4, close to 0. So be careful of when you are, again, snapping the picture. So let's wrap this up. References. I like some of the stuff I read at Engineering Dynamics website. They're in San Antonio. They also do presentations in the spring and fall here in Houston at the Texas A&M shows. They got symposiums for rotating equipment and also for pumps, and they have tutorials there. And I've learned a lot of stuff from this website. Engineering Dynamics, right here, technical publications. I'm not endorsing what they write here, but I've used a lot of their information. They talk a lot about, they deal a lot with reciprocating compressors. So they're talking about displacement, but they talk about the other pulsation and fluid flow issues in piping systems, and they're focused on piping systems. If you want to go to their website, list of all publications, read through that stuff. A lot of good stuff there. Again, there's a lot of good sources for this type of information. They do talk about, again, those stress concentration factors. You also see stuff on stress concentration in like the DNV codes. Okay. Now, again, what we're talking about here is that this is forensic engineering, not design engineering. You've got a real live system out there that's wagging back and forth, and you want to evaluate the magnitude of that problem. If you're looking at a brand new system still on paper, well, use screening for that design, not harmonic analysis. What are you going to guess a magnitude of deflection or guess a magnitude of a force? You're going to guess a forcing frequency? No. What you're going to do there is what I talked about back in May. You will calculate natural frequencies and keep those natural frequencies away from troublesome frequencies, like get everything above 5 hertz, for example. Okay. Well, we're about halfway done with what we can do on dynamics quickly as far as capability. We did modal analysis. Today we did modal harmonic analysis. Next we'll be on seismic analysis. That'll be later in the year, and then we'll have the time history analysis after that. Okay. Because you've persevered here, you're entitled to our PDH certificate. You can request this, and we will send the PDF to you. You put your own name in there, and then sign it down here. This is what it is. It's a method of documenting your work, or just remembering that, yep, I did that 1 hour of PDHs with Intergraph on January 30th. Okay. So thanks for your attention. We've got a few minutes left. I want to run through Caesar 2 input processor really quick to show you how this all tags together. I was just showing you screenshots. So before I turn it over for Q&A, I just want to briefly review the Caesar 2 input. Okay, so here I am at the main menu of Caesar 2. I'm looking at the job called inlet piping. That's the model I was looking at today. I'm going to go look at the input real quick. There's my model. There's my node 1090. My fatigue curves, they're already here. I'm going to read them in again. Let's get it right there. Yeah, let's get that. And we now have them resupplied. Okay, that's the only change in my input processor. I'll run the analysis, static analysis. And then I can take a look at the, in a second, take a look at the dynamic input processor. Okay, I'm not even look here, statics. Dynamics, right there it is. Harmonics, there's my excitation frequency range from 5 to 6 by 0.05, and there's that 100 million. I did not specify any force. I specified only that displacement, 1/10 of a millimeter in the X, phase angle 0 at 1090. And my control parameters, there's that 1% critical damping. Now when I click the running man, it says okay, then it goes on to the analysis. And here are the 21 maximum displacements. It's all 1049. There's the maximum response. There's that 2 millimeters. And there's that phase shift. Okay? And again, I'm not even going to read that stuff. I'll just say let Caesar 2 select them. So here are the 21 that the program selects. And I'm in the opposite, so I could take a quick look at this one. Here we'll get fancy. We'll take a look at animation. 5.65 and view that. There, that's pipe wagging back and forth. That's the problem, okay? It's only like 2 millimeters, but there you have it, okay? And of course, I've got the stresses available too. I'll look at that one. Stresses, view that. And there's the allowable stress. That's fatigue. Again, this is a fatigue report. All right. Now I'm going to go do it again, but this time I'm going to select my own frequency phase pairs. Run it again. And this time, user selects. I'm going to pick, how about that one? Review current frequency, 5.75. And I'm going to look at node, well, let's look at that node 1049. Well, how about 1050, just a different node. And apply. And we see here, the phase angle is a little different, but it still follows that same pattern. Double click on them to highlight them. I'm just going to pick these peaks. And return, and we're done here. We picked 4. And here are the 4 that I picked. Again, you see the relationship of 90 degrees between each one of these. Continue. And now I'm at the output processor, and I'll just look at the displacement summary. And let's go to our 1050. There it is, negative 0.63, just about 0, positive 0.63 and 0. All right. So that's how we can use that processor. Very quick processor. Okay. All right. Rich, do we have any interesting questions that we should bring up right now?
Yeah, a couple of them I haven't had a chance to answer, so we can start with those.
Okay.
Okay, here's one. What about the harmonic analysis? Hang on, the screen's moving around. What about the harmonic analysis in the earlier design stage before the problem occurs?
You can run the program, but what are you going to use for your input? That's my issue with that. it's kind of like today. They're still building bridges that end up having resonant problems. Well, it's not exactly the same thing, but you could talk about the Millennium Footbridge in London. That had a vibration problem. It was caused by humans, but they didn't predict it. And I find it difficult to find out how you could predict that to happen in the first place. If you know it's going to be a problem, you avoid it by stiffening up the system in the first place to keep the natural frequencies higher. In my situation, in the model I had here, if I had a pump that was running at 300 RPM or whatever, 330 RPM, I would make sure that the first mode of vibration was above that, but I don't think I would go around fooling with harmonic analysis to evaluate a possible load because you are so uncertain of the natural frequency of the system. That's why we work off the ratio of the forcing frequency to the natural frequency and sweep through a frequency range. But if you have the data, try it.
Okay. Here's another one. Way back when you started, there was a question, where did the 0.1 millimeter displacement come from?
Oh, yeah, and I said I don't want to talk about that. You know, there are, ASME has some charts where they show you the maximum, basically rotating equipment nozzle displacements associated, or velocities associated with certain driving frequencies, and they talk about this is not perceptible, below this line is within design, above this line is danger. I don't have enough experience to talk about where that number comes from. I know a lot of users put instrumentation on their piping, and they can tell you how much a nozzle moves. That kind of information. I've seen a situation where they could put, with a strobe light, they can start to estimate the deflection. I'm just saying, if we keep it in the forensic side, it actually becomes quite qualitative there as well. Depending on if you can match the shape of the nodes that you're interested in, I think we're going to see a lot of amplification no matter what the applied deflection or load is in the piping system.
Okay.
I don't want to, I've said more than I should already.
Okay, here's one. What about when you want to evaluate a new design, to evaluate if the piping is sufficiently restrained?
Well, again, I get back to that's that modal analysis point. You can't use a very sharp pencil to evaluate this in the design mode. Qualitative analysis, calculate natural frequencies, and make sure you are not anywhere near a known forcing frequency. But then you got situations where, let's say, well, in our PV Elite software, we will calculate the critical wind speed for your column. So what do you do to avoid that? Well, you put strakes on the column to disturb that wind pattern around your vessel. So they're getting back to piping, though. Calculate natural frequencies and avoid those forcing frequencies near those values.
Okay. How to decide whether we have to do harmonic analysis or not?
Something's wiggling at a cyclic. There's a cyclic response in the field. The hard game, Caesar 2 is the easy part. The hard part is getting that magnitude and determining where to apply that vector, whether it's a force vector or a displacement vector. That's the difficult thing, in my opinion. Is it caused by pulsation? Is it caused by equipment vibration? Is it caused by fluid flow?
Okay, and that's another question. How can we model in Caesar for flow-induced vibration?
Well, again, flow-induced vibration, you're going to use the force tab, not the displacement tab. And I did this many years ago. Again, if you have the system out there in the field, you're trying to reproduce the numbers that you see out there in the field. Usually, if it's flow-induced, you're going across an opening or through a orifice, and that would be the point of application. And the vector that you supply, the force vector, is perpendicular to the direction of flow. Okay? And the magnitude, I think you just have to jimmy that number until you finally get the observed response. Again, in the forensic side, if you can get the response to look right and the shape to look right, then the bending stresses are probably correct. I'm going to say it that way. Just ramp up and down that force, or adjust your natural frequency to forcing frequency ratio until you get the response you want to see. Again, I'm going to look at output to say that the input's right. So I don't have a guess for the magnitude of that load.
Okay, we've had a couple of questions on that reference book you cited.
That website, Engineering Dynamics.
No, I think they were talking about the textbook. You had it in an earlier slide.
Oh, that's what I used in college. It's still in print. Thompson, Theory of Vibration with Applications.
Should be available on Amazon, right?
Yeah. But, you know, there's a ton of books like that. I always get a kick out of it. When I look at books that I still use from college, I think that's on page 47 of that book. I never get the high numbers, the fancy stuff. That was just forced vibration, basics in forced vibration.
Okay, and I guess maybe one more since it's 11 o'clock here.
Yeah.
What is the relationship between the forcing frequency and the natural frequency? Do we have one?
Well, heck, that's the heart of this whole thing. As they get closer to equal one another, that's when things just resonate. That's resonance and dynamics all wrapped up into one. And that, again, that's your kind of wild card here. I use the analogy of a radio. The old analog radio where I turn the dial to tune in a radio station. And I will, talking about the old analog radios. Now, what am I doing when I'm turning that dial knob? I'm changing the natural frequency of that circuit in the radio. And I have a given forcing frequency coming through the airwaves, okay? That's the electromagnetic excitation. And I just adjust the ratio between the two to listen to the radio. In the same sense, we're adjusting the ratio in Caesar 2 to get the observed response. Again, that's why, again, I'm saying it's more forensic. But how close do you have to be? Well, I said earlier that there's the wild card is damping, but also there's three terms that combine to give you the magnitude of the response. There's the applied load, there's the damping ratio, percent critical damping, and the ratio of the forcing frequency to the natural frequency. And I can tune my piping system the same way I can tune the radio, but to one case I'm tuning the system, the other case I'm tuning the applied load.
Okay,
that's the heart of it.
Yeah, maybe one more question here. And this has come up a couple of times. How do we get the displacement information from the actual piping installed at the site?
Again, I don't want to have a very sharp pencil when I do this. So I might get an answer that, oh, we're overstressed. I'll want to change the natural frequency. But again, you can instrument and put accelerometers on the line or use a strobe to collect that data. I'm not an expert in that, but there are sources of that type of information to accumulate data from the field at different points, critical points in the system. I would say in many cases it's somebody's out there, some operating engineer says, that pipe's wagging all over the place and it's always happening. Is it a problem? And that's why then they'd come back and say, well, would you guess how much it's moving there? Well, it's moving a half an inch. Or you see a scratch on a plate or something like that. Oh, well, that's how much it's moving. And work it back from there. Again, I'm back in the office, not in the field, and collecting this data.
Exactly.
All right.
Exactly. All right. I think we have to wrap this up. It's been the hour, and anything that wasn't answered, we'll go through the questions, answer them, and make them available to everybody who attended.
Great. Well, thank you everyone for attending, and we'll keep up some more of these as we go forward. Thank you.